which includes another definition. So if such a phi as above is an L monomorphism and also it's onto, so it's a bijection, then the same as with rings, groups, etc., phi inverse is also L monomorphism. This is easy, tracing this definition. Just for the first part, one would have to observe something. So it's not like with continuous functions, for example. Continuous function, which is bijection, the inverse does not have to be continuous. So it's like doing algebra, okay? Kind of intuitively, not doing topology or geometry. And then, so that's the remark. And then definition part. And then we say that this is isomorphism. Or L isomorphism. Yes, in practice we skip this L, but sometimes we don't. If you want to make sure this is isomorphism of groups or rings, then we kind of say, what is this L? Denoted.
Why did you give the definition of monomorphism but not homomorphism?
Yes, I was trying to say, to be honest, I don't know a good reason, but for relations it's pretty strange. If function is not one-to-one, that I think doesn't make much sense to say it's a homomorphism if we consider relations. But yes, so somehow people don't define in this general context homomorphism, but I cannot say now what really breaks if you do. Also they are not very much useful in this generality. Yes, because the most important notion will be of substructure and then some elementary extensions, and it all is one-to-one there. So we will come to that. Or denoted like this. So some lemma, which we'll again not show, but often use. So short saying will be that isomorphisms preserve the truth. Okay, so formal statement is, if we have a formula with some free variables, and elements in the first structure and psi is this isomorphism in this sense, then it kind of preserves the satisfaction of this formula. So alpha after we plug M1, Mn for these free variables holds in M if and only if the same happens in N after we put psi to this parameters. Yes, in particular, if this formula was a sentence, then it's true in M if and only if it is true in N, because there is nothing to plug. So again, as many times before, so proof is by induction on complexity of formulas. And we skip it. Yes, we skip everything which actually requires the formal definition of formula. But the remark, which we kind of used already in problem session, so in particular, what I exactly said, isomorphism implies elementary equivalence. Okay, the truth, but this is much stronger. Okay.
Because of the kind of the argument.
Yes, it's not the same. But still, soon we will see examples that it's not the same. So finally, the notion which I was really aiming at, maybe quicker, but I also needed so I really need that notion of isomorphism and of substructure, but this one contains both. So M is an L substructure of N. So of course, if universe is a subset of bigger universe, and this inclusion is a monomorphism. So that's pretty formal, so let us write what this means. That is actually this is a definition which in algebra I don't like. Let me mention it later. That is for all f in f Fn extends. Okay, this notation means that Fn restricted to power of m is Fm, but formally it means that graph is contained in the graph for all R in R. So that's the difference, kind of. This is not a subset, not only a subset, but it's exactly the intersection. And of course, for constants, it's just the same interpretation. So this is the moment to answer the question of the guy who didn't come today. Why did we call our language the language of rings? To make sure that substructures are subrings. Okay, so examples. So if G is a group, okay, then we can regard it in at least 3 languages. G a group, let L1 be this. Okay, so this is just binary function for multiplication. This is also language with constant for neutral element. And this also has unary function for inverse. So all is kind of the same. G is a group in all of these languages. And if it is a group, you can always define uniquely this and this, so not much difference, but the notion of substructure changes. So if you care about substructures, so here, and L1 substructures of G, okay, and I don't care now, I denote by the same letter G and its universe, are subsets of G closed under. Okay, so they don't have to be subgroups, like natural numbers in Z plus, or even numbers greater than a million in Z plus are also closed under plus. Better example. Okay, so the word would be perhaps sub-semigroups. So this good name would be language of semigroups, I guess. L2 substructures of G are subsets of G closed under and containing neutral elements. Still, they don't have to be subgroups. Now, like N in Z. So one of the names could be submonoids or subsemigroups with identity. And just in this third language, substructures are really subgroups. So let's just do the same for a ring to get to our case. So if R, let's say ring with 1, okay. By language of rings, probably I should have been saying language of unital rings, but okay, then if we have L1 like this and LR, so maybe L, no, plus times. Then L substructures of R are subsets of R. Okay, and containing 0, 1, so something like sub-semirings. And finally, LR substructures are exactly subrings. Okay, so this was a bit long example, but also justification of names. Why do we give particular names to particular languages? But also often we forget, people could say this is language of groups, this is language of groups, this is language of groups. But most careful people would say this is language of groups. And okay. Finally, the interesting notion last definition. So M is an elementary substructure of N, and this is denoted like this. If it is a substructure, but also it preserves the truth of sentences with parameters from M. So that's a really strong condition, and for any L sentence parameters from M, we have that it holds for any L sentence phi okay. So first I will give some remarks about it and then some non-examples. At this moment it's not easy to give any example of it, well, except trivial, except if M is equal to N. Yes, because to give example, we kind of have to know the full theory of it, even with all the names for elements of M. We will get some examples later, but it's never easy. So what are the remarks? So first, this is okay, all these remarks are aiming to say this is something stronger than elementary equivalence. So one. So if M is a substructure of N, then it is elementary if and only if theories are the same. Okay, if you remember this notation, but with the language containing parameters from M, exactly like here. Yes, not just sentences in the original language, but we are allowed to put parameters from this smaller structure M, which are of course naturally interpreted here. So it is something more. So it implies but we will see that it's not the same. Okay, so let's see some non-examples first. So almost anything you just take will be not, almost any substructure taken at random will not be an example. For example, R is not in C because yes, here we have square root of -1, here not. Okay, and this seems to be using parameter, but it's not using 1 is the constant from the language, so even also this holds, which is here stronger.
State that it is independent of the theory, this concept of elementary substructure.
In which, yes, okay. I mean, it's about structures only. There is no underlying theory, yes. But usually, in practice, it is. We are taking subgroups, subfields. I mean, if we take a substructure of a group which is not even a group, then of course it's not elementary, but it's a kind of morally, okay, formally not, but morally there is some bigger theory around always. But yes, formally it's only about structures.
It doesn't use parameters from C?
No, it doesn't use parameters from anywhere here.
Not nowhere. -1 is not a parameter.
What if you write -2?
It is still not, okay, it is both.
-1 plus -1 is -2.
So you can define -2 without any parameters, without only with only constants, constant symbols.
What did you say?
So -2, yeah, -2 is defined as, let's say, minus.
Okay, but if you write minus the square root of 2, then
Square root of 2 is something which depends on the, okay, it's the difference between definable and algebraic closure. Okay, so, okay, this is like a term. You can define it something like this. Is a part of language.
okay.
And it has interpretation in every LR structure. Unique interpretation. Okay? So constants are also like this, and this is very close to being a constant.
Maybe I didn't understand parameters.
There will be example, maybe. Third example will use a parameter, which will be also 1. Okay, but so I will do more precisely third example that I plan. But still, okay. Okay, so here I should say, but we understand I'm talking about rings or fields. This, but again, they are not even elementary equivalent. Well, since this is dense, so for each maybe. But it's not true. Yes, the ordering of natural numbers is not dense. You cannot put anything inside 0 and 1. But still there were no parameters as here. So even so now finally example when even the smaller structure is isomorphic to bigger, but it's still not elementary substructure. And now we will see this parameter. So in the same, so of course here L was language of rings, here L was language of orders. Again, so I'm saying that natural numbers greater than 0, for me natural numbers include 0, is not so what is the statement? Now I will use parameter 1. Okay, it's not in the language. There are no constants in the language. And the statement is well, for all x. This particular one has an element here. Not to be confused with this one, which is yeah, that's that may give some headache because we have I guess here it should be really written 1n if you want. I could write once, but the statement is like this. The sentence is like, no, I could, but this is also okay.
Yeah, but if you write 1c, then
this is also okay because then I interpret this element as this. Then it becomes actually a sentence with parameters from C, which exactly the same meaning. But yes, but here this one means really a constant symbol.
I was thinking to use another element. This is why I said the square root of 2.
Then there will be two possibilities.
It's not defined.
So then there will be just definable set, which there will be formula in your example. So I haven't finished that, but in your example it will be formula. Okay, it really will be formula E of x. Okay, and then the formulas, the elements which satisfy this formula, usually there are 2 of them in every model. Yeah, and that's it. And this is square root of 2, I hope, yeah. Okay. So here, okay, but this is true. So 1 is the smallest element in natural numbers greater than 0, but well, I could also put here greater, well, okay. So you see what happens if I try to write, and they should be up. Because it's a substructure, so 1 is the same.
You take the parameters from substructure.
Which are naturally interpreted. Okay, I should not say that. It's parameter from substructure is naturally interpreted in superstructure as the same element. But anyway, this is our real one. So here, 1 is the smallest element. Here, 1 is not. Because there is also 0. Okay, so it's not elementary substructure, exactly, but the function which you can guess, I guess, is an isomorphism. So In particular, they are elementary equivalent. So they are even isomorphic, but it's not an elementary substructure.
Now you use parameters.
Huh? Yeah, and they have, in particular, you have to use parameters to see it. Okay, still there is hope. So there were only non-examples. It's more difficult to give examples, but now using compactness theorem, I will show there are always many, abstractly, there are many examples of such situation. This is called upward Löwenheim-Skolem theorem. We will not need the downward one. What does it say? So let M is important is infinite. And again, take any cardinal number, kappa greater than cardinality plus cardinality of the language. So this is basically the cardinality of this language L extended by parameters from M. That's the meaning. Then we always can find like elementary superstructure of cardinality kappa. So there is something bigger, something that M is elementary substructure in N, such that and using this we will show this model theoretical theorem too. And some properties of fields. So proof.
Kappa is arbitrary, right?
Huh?
Kappa is arbitrary.
Arbitrary. Uh-huh. Just big enough. Okay. So we work in some language even bigger, that language of L expanded with constants from M. To L prime by adding new kappa constant symbols. Yes, some constant symbols which were not already there. So L has its constant symbols, there are extra constant symbols for all elements of M, and still we are adding kappa new ones. Yeah? We can do such things. So I think there are people who claim we cannot do such things, but there are not so many of them.
Why?
Some people believe only in finite sets, and this is really, really infinite.
Don't believe in magic.
There is very finite number of such people. Okay, so this is L prime, and define, okay, and L prime theory T prime, and to this theory we will apply compactness theorem, and its model will be this N. So this kind of full theory of M, even with constants from universe of M, and saying all the constants are pairwise different. Yes, so for all different pairs of indices smaller than kappa, this is still kappa, theory says interpretations of these constants are different. Okay, so now, okay, shall I? Huh? Huh?
It's not too hard or too technical.
Huh?
I mean, if the proof is not too hard or too technical, maybe we can think the rest.
The proof is not hard.
Yeah, I mean, we will just show that every finite set
Yes.
as a model, right?
Yeah.
Yes, yes, so you mean without writing, or what?
Maybe it might be a problem.
Think the rest. Okay, there were enough. We could think. Okay, then show. Okay, then problem. Okay. Which problem 13? Show that T prime is finitely satisfiable. Okay. So now, by compactness theorem, there is a model of T prime, and problem 13. Okay, so then by this, by remark, not only that, there is a model of T prime, but still this T prime, okay, the L prime, now the cardinality is exactly kappa. And by compactness theorem, there is a model such that, so this is the moment, actually this is a bit important, this is the moment when I need this bounds from compactness theorem to get the model of exactly cardinality kappa, okay? So this I don't want to skip. This was kind of, because you could think, why did I care about it? So this is a moment I cared about the bound, which will be important later.
It's also smaller than kappa.
It's also, yes, but now we see, okay, so here we have this is smaller than kappa, but since n, then it's also at least kappa, of course, by this. So it's exactly kappa. That was the part, okay? So compactness theorem gives us many, maybe not substructures yet, but like elementary extensions of arbitrary, and now I may show, okay, the time. I may start at least. So using this, I may show this theorem, which was called MT2. This was crucial for Hilbert-Nullstellensatz. So any extension of algebraically closed fields is elementary. So this will be something concrete. First real example that such things happen. Okay, this was needed for Hilbert-Nullstellensatz, but it takes a bit more time that I have left. So let me start. So let Fm extension of algebraically closed fields. So what is the trick? Now we take kappa. Okay, now of course I don't distinguish between universe and fields. So take kappa greater than this. In particular, kappa must be uncountable, because algebraically closed fields are infinite. And we apply upward Löwenheim-Skolem theorem. There are extensions here, elementary. So elementary extensions in language of rings of fields. Such that they are all of cardinality kappa. Okay, but now there is a moment, so these are such extensions. So in particular, we have such extensions, and cardinality of f is smaller than kappa. And now, okay, now it's a moment, how much do you know from field theory? Because now I want you to conclude this is problem 14. Okay, that this plus, okay. In this context, it implies that there is an F isomorphism psi. So this is something specific to fields. Okay, so we use that f prime and prime are algebraically closed, and okay, so I'm giving here a kind of hint plus what kind of things you have to know from field theory. And that's the transcendence degree of must be kappa in this case, and transcendence degree is the cardinality of maximal algebraically independent over F subset. So did it appear in your life? We can discuss it in problem session. Okay, so that's that you should. So still there is something, okay? So I'm saying it's kind of obvious that by the assumptions, transcendence degree is the same kappa, and knowing that, you should conclude that then they must be isomorphic over this field F. Okay. And then, if we know that, okay. So I will just give a sketch and finish and come back to this next Thursday, because this is actually something quite interesting. What's going on here? So we have commutative diagram. And using this, if you have a VLR sentence with parameters from F, then you can just go around this diagram. So it is true here. If and only if, just by definition, it is true here. But then, since also Psi preserves parameter from F, it's if and only if it is true here. So this is this isomorphism preserves the truth. And then again, so we get this is true here, if and only if it is true here. So, okay. I will repeat it a bit next time because it was too quick. Okay, and then comment a bit more. But this is so. Okay. Okay, so I will, but you can see that really the crucial thing, in fact, was compactness theorem. Thanks to it, we get this Löwenheim-Skolem to find such things, these bigger ones, where truth is the same, kind of, and then properties of algebraically closed fields told us there must be this isomorphic here, and combining all of this is giving us this second theorem, which was crucial for Hilbert-Nullstellensatz. Okay, so thanks.